Now in the last video we have seen derivative of function with respect to some independent variable x. That is, if my function is y, then derivative of y is dy by dx with respect to x, of course. Now I'm going to write here y and its derivative dy by dx. So now we found that if my y is equal to x raised to n, then dy by dx is n into x raised to power n minus 1. That is what we kind of proved, I would say. Now trigonometric functions. If my y is sine x, the derivative is cos x. If y is cos x, it is minus sine x. If my y is tan x, then it is sec square x. If my y is cosec, it is minus cosec x cot x. If it is sec x, then it is sec x tan x. If it is cot x, it is minus cosec square x. These are the trigonometric functions and their derivatives. Correct? Now if my y is log x, then its derivative is defined as 1 upon x. If my y is a raised to power x, then its derivative is log a into a raised to power x. Now here I can have e raised to power x. Now what is that e? E is the Euler's constant. Okay, and if it is e raised to x, then derivative of e raised to x is going to be e raised to x into log of e, but then natural log of e is going to be equal to 1. So if it is e raised to x, then its derivative would be e raised to x. But then it is just a special case of this result. Okay. Now you would be having a question like, I have just stated, okay, who told you that derivative of sine x is cos x, or derivative of tan x is sec square x? Okay. In mathematics and physics, whatever you say, you should be in a position to prove. Correct? In the last video, we have seen that derivative of function y with respect to x is equal to limit of, or then I would say, instead of calling y derivative of y, I would say derivative of this function f of x. Fx is a function of x, so d dx of fx is limit as delta. Now instead of delta x, I am going to use h tends to 0 instead of delta x. I don't want to write that delta everywhere. So that is f of x plus h minus f of x upon x plus h minus x. So that is going to be equal to h. Correct? I am going to prove for this. Now let my fx be sin x, and I want to find derivative of this fx, derivative of sin x. So I'll have to put it in this manner here. Okay, so obviously if fx is sin x, then f of x plus h is going to be equal to sin of x plus h. Okay, so my derivative, now this derivative of f of x, I am going to call f dash x. When they write f dash, it is derivative of f of x. Correct? So that would be equal to limit as h tends to 0 sin of x plus h minus sin of x divided by h. Now here I am going to take liberty of using some trigonometric results. Okay, or the trigonometric result that I'm going to use it here is sine c minus sine d, and it is going to be something like this. It would be again that limit sign remains as it is, limit as h tends to 0. Sine c minus sine d is 2 cos c plus d by 2 sine c minus d by 2. So it would be 2 cos c plus d. My c is x plus h, d is x. So it is x plus h plus x upon 2 sine x plus h minus x upon 2, and then this whole thing divided by h. Correct? Now what you get here? You get x plus x, that is 2x plus h upon 2. So now I am going to, and what about this? You are getting x plus h minus x, so that x is anyway going to vanish. Correct? So what I have over here is limit as h tends to 0, limit as h tends to 0. I am not writing this 2 right now. Just see what I do. It is cos of x plus x, that is 2x plus h upon 2. I will write this as x plus h by 2, okay, sine of x minus x is 0, so h by 2 divided by h. That 2 which was in the numerator, I am going to take in the denominator of denominator. Correct? So I'll write h by 2 here. Now what? Now now see, there are certain rules of limits that I'm going to follow here. Now you have to follow me for this for the time being. Okay, so this is equal to limit as h tends to 0 cos of x plus h by 2 into limit as h tends to 0 sine of h by 2 upon h by 2. Now this quantity, okay, this quantity is sine of h by 2 upon h by 2, okay, and then limit as h tends to 0. See, as my h tends to 0, h by 2 also tends to 0, correct? This quantity, its value is equal to 1. Okay, I'll explain you in a while and in less than half a minute. But before that, now here, what is cos of x plus h by 2? And if I apply, now I don't have anything in the denominator, 0 in the denominator, right? I'm not having any physical quantity which is tending to 0 in the denominator. So I am now I'm fine. I can substitute that h by 2 is equal to 0, and what I'm left with here is nothing but only cos of x, and cos of x into 1, which is finally equal to cos x. Derivative of sin x. So if fx is sin x, its derivative is cos x. So I have proved this. Now it is your exercise to prove this. About log x and 1 upon x, you will be learning that in your math classes in detail. In fact, you will be doing everything there, but then at least these trigonometric quantities you can practice here, using the same procedure. Okay, now coming back to what I was saying over here. Now you can use your calculators and just try what is sine of 1 degree. Okay, but now again we have we know what is a radian measure. This h by 2 and this h by 2, sine of h by 2, you have to take that 1 degree, okay, 1 degree that 1 degree angle you have to convert in radian and then take sine of that. Okay, and just see what you get. Okay, so 1 degree in radian and that same value here, you will find that sine of 1 degree taken in radian is equal to that 1 degree, okay, in terms of radian. So that ratio is going to be equal to 1. You take, and that is even for 1 degree it is true. For half degree you try, for quarter degree you try, for 0.1 degree you try any value. When your theta is small, limit of, so limit, I'm going to write it over here, that small, I'll put it over here, limit as theta tends to 0, theta in radian, sine theta upon theta is equal to 1. You can find this, you can prove it for yourself, right? So that is all about basic derivatives of basic functions here. In the next video we are going to talk about integration. Thank you so much.